Okay. Hello, thank you for attending the session on privacy preserving record linkage. Nearly 50 people in the audience. That's quite impressive, I think. We will start today with Josie's presentation on data linkage and the official statistics in the UK. Josie has a strong background in evolutionary biology, and due to her interest in statistics, she switched to this exciting field of privacy preserving record linkage. Thank you very much. And Josie, your turn.
Thank you very much. Okie dokie. So, hi everyone, I'm Josie Plachta. I am a methodologist from the UK's Office for National Statistics. I specialise in data linkage techniques and their research. I'm sharing with you today our recent project in designing a linkage algorithm that works on hashed datasets. And these datasets consist of hundreds of millions of rows of data. So our feelings towards hash data is very much synonymous with the phrase, if life gives you lemons, make lemonade. So nobody really wants 1,000 lemons, and we don't really want to be working with hash data, but it is what we are given. So rather than saying we can't link that, we wanted to come up with a method that at the very least would enable us to compare linkage of hash data to in the clear data results. There are several key data sets for the ONS outputs that are affected by this move to hash personal identifying information. Due to the short time, I will not go into detail about our hashing algorithm specifics, but feel free to ask us questions if you are interested. So the first data sets that my teams used for this research project are the UK's DWP Customer Information System, which contains information on UK residents, so England, Wales, Scotland and Northern Ireland, who have benefits or pensions, and we'll refer to it as SIS. And it's around about 108 million entities. It's used in many ONS statistics, so employment and economy. And in 2019, for the first time, we received SIS in hashed format. And we linked it to the NHS's Patient Demographics Service, which we refer to as PDS. So although we hold PDS in the clear for permission to link it to SIS, we're required to hash it as well. So the PDS only covers England and Wales, and it is anyone who has interacted with a GP or a hospital, and it contains around 88 million entities. So to design the linkage method, we had to use in the clear proxy data, seeing as we don't actually have access to the SIS data in the clear. So to do this, our proxy data sets were the 2011 census data and a historic version of PDS called the patient register. So in general, when we try to link data, we often come across challenges that are called data errors, so incorrectly recorded names, scanning errors, etc. And in the clear methods handle these really easily with string characters, nickname lookups, and the intuition of clerical matchers who look at the data and make these decisions. However, hashing data hinders these methods, as once hashed, any similarity between strings is no longer preserved. So if we take our first example, say for example, our linkage error revolves around the name Catherine, where in one data set she's written her name with a C and one with a K. And within the clear methods, you could perhaps see that 8 out of 9 of the characters shown in green are the same, and you could code an automatic rule that matches her. So say 70% of characters match, then agree, then match. And a clerical person could also use their intuition to make this link. However, once it's hashed, you can see that we are only left with a single matching character, so the green G. So there is no similarity preserved in the hash. And we also run into problems with non-name variables. So for example, if we take date of birth, due to security concerns, we're not allowed the components of date of birth. So we get a single full date of birth variable hashed. And once it's hashed, there is no way to extract the components of date of birth. Thus, if a single one does not agree, we cannot see any similarity between our date of birth hashed strings. So our solution was to extract substrings for each of our variables prior to hashing, and then we can link on these. So for example, we might have the forename variable of Christopher, and we might derive a nickname using a lookup. Then we might take substrings, so the 4 letters, the last 4 letters. We might use phonetic codes such as soundex and double metaphor. And we now no longer need agreement on the full Christopher. We just need agreement on one of these derived variables to help us match. So in total, we ended up with 57 derived variables. And to choose these 57, we used our proxy data to establish which of them gave the best balance of the most correct matches without, while attempting to completely leave out any incorrect matches. And those of you who regularly design match keys may now be considering how to account for all of these match keys, for all of these variables in a match key format. So with just the name variable alone, you would end up with nearly 3,000 match keys to consider all of the combinations of the derived variables. And that doesn't even start to consider fuzzy date of birth or geography, or even transposed agreements, so sort of people writing their last name in the forename variable. But before we even start thinking about match keys, we have got so much pre-linkage to do when working with hash data. So because of all of this hashing and deriving, our method, although deterministic, follows a slightly different path to traditional deterministic algorithms. And the first diversion is just the sheer amount of pre-linkage work that has to be done. So this includes agreeing and applying cleaning and standardization rules to each and every raw variable. And this alone was not an easy task and caused a debate spanning 3 government departments about what to do with hyphens in name, which became affectionately known as hyphengate. Next, our derived variables have to be agreed upon, and a balance needs to be sought both in terms of security, so the more variables we have and the less entropy in them. So for example, an example of a variable with low entropy would be month of birth, as it only has 12 values. So less entropy is bad for security, but also our data suppliers will have to code all of these cleaning and derived variable requirements. So there's also a lot of resource that they have to put into this. And all of this pre-linkage has to be quality assured. So we need to ensure that our data supplier's code produces the same output as ours. For example, if they were hashing Mary Beth with a hyphen and we were removing the hyphen, then we'd never be able to match these records, as once hashed, they would not agree. So this involved testing our outputs on shared synthetic data, and we did not find any of this particularly easy. But once the pre-linkage was successful and we'd received some hashed data, we were ready to link it. So the first stage was a method often seen in probabilistic algorithms. So we create candidate pairs of records by loosely blocking sys to PDS, and this produced over 1 billion candidate pairs. And next, we used our derived agreement to measure the strength of agreement had for each of the raw variables. So this derived agreement measure is how we bypass having thousands of match keys. The measure is currently done categorically, with agreeing derived variables either indicating exact, strong, or weak agreement. So the level of agreement that each derived variable gave had been thoroughly researched on our proxy data. For example, if a pair matched on full name, they received exact agreement. If the sound X matched, then strong, and if the last 4 characters agreed, then weak agreement. So our match keys now differ slightly from traditional rule-based matching in that they operate on this derived agreement rather than the variable itself. So an example key might be strong agreement on forename, weak on middle name, exact agreement on surname, strong agreement on date of birth, and exact on geography. And then any of our candidate pairs that match on these rules are classified as links, and those that are not linked by any match keys are classified as non-links. So we have 44 match keys in total, and they are run in hierarchical order, with the strongest matches being made first. The cleanup stage consists of ensuring that records that have been matched to more than one candidate are retained for the strongest match keys and dropped for any weaker keys. Where multiple matching occurs within the same key, all matches are dropped. We also produce a table of linked pairs and 2 tables of unlinked records. And finally, we undertake a QA, which requires our data suppliers to be willing to provide us with a large sample of in the clear data. For the sys to PDS linkage, a sample of 600,000 unlinked records was provided, and a sample of 2,000 pairs from each match key was provided. So we use these samples in the clear to estimate our linkage accuracy, and the result of our hard work and intensive collaboration was a pretty good linkage accuracy, with our estimated precision and recall being pretty damn high. So we estimate that there were around 68 million true matches in our data, and we successfully linked 64 million of them, leaving between 3 and 4 million mismatches, and we think around 36,000 of our links were incorrect. We also use confidence intervals to estimate what our precision and recall would be at 95% confident, and found that these metrics were also pretty high. So we think that we got a precision, so that is of all the links that we made, the majority were correct. So our precision we think is 0.99, and at the lower confidence interval we think it's 0.98. And our recall, so this is the number of true matches that we linked, we think we got a recall of about 0.95, and at the lower confidence interval we think about 0.94. Now, we would also be really interested in looking at the biases of our linkage. And traditionally, bias is analysed by comparing the distribution of errors between different groups of interest. Low bias data sets have evenly distributed errors, and biased linkage results are clustered in particular groups of interest. Now, since we've only ever seen a relatively tiny sample of the SIS data, the number of errors we've actually observed is tiny, and as such, we can't imply anything about these errors distribution. So to use an example from our data, we have a graph here that shows the percentage of linked records in different groups of interest. In this case, we're talking about the ONS hard to count index, which is designed to rank geographic areas for census in terms of how likely they are to appear on our surveys. The index uses information on things like ethnic composition, economic activity, and deprivation. So on the x-axis of our graph, we have 5 ranks of hard to count, with records in rank 1 areas on the left being the easiest to count, and 5 on the right being hardest. We also have a 6th group where the hard to count rank could not be attached, mostly due to records having invalid or missing geography. On our y-axis, we have the percentage of records in PDS, the blue section of each bar representing linked records and the yellow representing residual unlinked records. Now, at first glance, it might appear like we do have a bias issue here. However, of these unlinked yellow records, we do not know how many of these are genuine non-matches, i.e. records that truthfully are not in SIS, and which of these are our 3 million missed matches. And nor does this tell us how our 3 million are distributed. And we're very keen to hear suggestions on how we can try and prize out our errors and produce actual bias estimates. So that's the bulk of my talk. We truly and deeply believe that sharing data in the clear is preferable for so many reasons. But if there is no other option and linkage must operate on hashed data, derive and conquer can be used. But departments must be prepared for the huge amount of resource and collaboration that's required for each linkage. The derived variables and match keys must be tailored to each datasets. We did manage to design a pretty effective algorithm, but it only works well for SIS to PDS. So some of our colleagues attempted to use this method on the HMRC's self-assessment dataset, and they did not even make enough matches to warrant doing a QA. So I think of the 56 million census records they tried to link it to, only 15 million ever linked. And this is not enough for the analytical purposes of that linkage. So from this and from our own observations, we predict that hashed linkage will run into severe difficulty when working with low quality data. So thank you for listening.
Thank you very much for this excellent presentation, Josie. I don't see any questions in the chat currently, therefore I'm asking one question. In the actual census procedures, how do you think these huge amount of unlinked records will be handled? Are you doing a second linkage using different data sets, or are you doing just a statistical estimate on the correction on the estimated results, or will be a huge fieldwork effort to resolve the unlinked cases?
In the census to
Yes.
self-assessment linkage,
Yep.
as it's not my team that's doing that linkage, so I'm very sorry I can't answer that.
Okay, I try to read a question. Wait a second. I'm unable to read a question. That's strange. One moment. Oh, someone simply asks for a definition of in the clear data, Josie.
Sorry, what was the question?
Josie, please define in the clear data.
Yes, my apologies. So in the clear data is just sort of, there's no hashing, no encryption. The variable address has 23 North Road and then the postcode in the clear. So yeah, you can see all of the information that was originally put in without any kind of obfuscation or encryption.
Okay. I hope you can still hear me. And in this case, we simply go over to the next presentation, and that will be Anna. Anna will be talking about the recent experience in Australia on using Bloom filters for privacy preserving record linkage. And Anna has a strong background in mathematics, is working for many years in privacy preserving record linkage and record linkage in general, and has a strong interest in criminological research questions. So Anna, please take over.
Thank you very much, Rana. I have to say I've been suffering some technical issues, so hopefully everything will go fine. I need to share my screen. Bear with me, folks. This one. And hopefully you can see that, and I'll just put it in. Does that look like is the slideshow, can someone tell me if the slideshow is actually working?
Yeah, I can see it.
Is it in slideshow mode? Is it in the presentation mode?
Oh, no, it's not.
You have to press one additional key, full screen.
Aha, okay. Right, can you see that?
Yeah, fine.
Terrific. Okay, right. Thanks, Rana. Hi, everyone. I'm Anna, and my presentation is reporting on recent Australian experiences in the use of privacy preserved record linkage, or PPRL, using Bloom filters. I guess a useful place to start is to really think about why we use PPRL or why we need PPRL. And I guess in an operational sense, the reason we need it is that some data sets, especially those of us who are in the operational world, know that some of those data sets are very hard to include in data linkage. And my simple view is often that's because people, custodians or data providers, either can't share their data or won't share. And by can't share, I mean that there might be legal reasons why they can't share. There might be laws that prevent the release of personally identifying information, or sometimes there aren't any laws that prevent, but custodians are very risk averse, and so they will judge the risks of sharing too great, and so not release data for, and I mean name identified data for record linkage. And the typical response when that is the case is that it's too hard or not possible. And so the data sets or that custodian won't participate. And as a consequence, the research will be limited and the insights from that research will be limited. And so that's where a PPRL really is born, or the advances in PPRL have really come to overcome some of these issues. So the PPRL that I'm talking about here is just one solution. There's different ways you can do PPRL, and it's not here that I'm going to be talking about those. It's the one implementation that I'm referring to here is the one we've adopted at the CDL, which is to use Bloom filters inside a probabilistic record linkage framework, the Fluji-Sunta model. We've adopted that model because it fits operational use, and by that I mean that it fits the trusted third-party model that we use for operational linkage in many countries. It has linkage quality that is comparable with name identified data or using name identified data. There are sufficient privacy protections in that model, and the model is both pardon me, efficient and easy to use. As I said, I'm not going into that, although Sean Randall is presenting at this conference too, and the link there or the reference to his presentation that talks a little bit more about the methodology and the quality, the linkage quality, is somewhere you can go if that is of interest. What I'm going to cover is some use cases, obviously not all of them, and certainly not in a 10-minute slot. So I've kind of tried to classify the use cases into three types of use cases. This is Buff, the bush kangaroo, Skip, the buff kangaroo, not the bush kangaroo, but the buff kangaroo. So the use cases, I think I'm just going to touch on the problem that use case solved, or how we used PPRL to solve. What was the problem trying to solve? How we used it, what was the linkage model that we used it inside of, comment a little bit on quality and performance, and also talk about challenges, insights, opportunities. So the first use case is probably the kind of typical use case where you think to use PPRL, and that was a problem where we can't share. So laws in Western Australia restricted the release of, or limited the release of name identified data from the Department of Justice. And this was part of a large whole of government project called SIDA, the Social Investment Data Resource. So Justice were not able to release name identified data for that project, despite wanting to be part of it. And so PPRL was offered as a solution. So it operated inside a typical trusted third-party linkage model. So there was a group that did the linkage. And but it involved, what was interesting is it involved internal separation of linkage. So some data sets were supplied with names, the justice data without. So that meant that the name identified data could still be linked using traditional methods. And then a second stage converted the name identified data into blooms, and that was linked against the bloom data coming out of the Department of Justice. So the linkage model also made use of a spine. So the name identified data was used to construct a spine, and then the other data linked to it using PPRL. What were the challenges in this use case? Getting the encryption tool out to the Department of Justice. They're not a typical user of linked data. They're not, or participant, a custodian or participant in linkage. So even to participate in linkage was a challenge, and having to get them to use an encryption tool was also a challenge, but overcome. And if anyone has worked with linking justice data, you'll know that that comes with its own unique challenges, such as there being so many aliases for a person. So in terms of linkage quality, that's still a piece of work that we're working on in terms of assessing the quality of that linkage. The second use case I've dubbed data sovereignty. And that's where, for people who are not in Australia, people outside of Australia think we are one country, but in fact we are 5 states and 2 territories, and each one of our states and territories has its own laws. So in this instance, we had research projects led by researchers wanting to link data across 2 jurisdictions where policies restricted the release of name identified data outside of the jurisdiction. And both jurisdictions, or both the Commonwealth that I've shown there in Western Australia, would not release name identified data to the other. In that instance, we used PPRL and had to introduce a 4th party. So neither the trusted third party in each jurisdiction was able to take up the challenge. So we introduced yet another linkage unit, another level of separation to undertake that linkage using PPRL. In these projects, these were, as I said, researcher-led projects. There was no opportunity to measure linkage quality because we weren't able to access name-identified data. But we did as much as we could to maximise linkage quality, and by that I mean we did not try to link inside an individual jurisdiction's datasets. They supplied us their linkage keys and we honoured those. We also used the Medicare ROM records as a spine, again, to optimise linkage. And I guess the challenge of note was gaining approval. It took almost 2 years for the first of these to gain approval, just because it was new to custodians, the PPRL, and new to ethics committees. And the third use case is probably the most exciting, I think, from my point of view, and this is the Holy Grail. There is an image of a Holy Grail, which is the desire to integrate healthcare data, both vertically and horizontally. And in this instance, I'm talking about the integration or the linkage of general practice data, so primary care data, either to itself, to other general practice data, or and that would be horizontal integration, or vertical, where you're trying to link general practice data to secondary care data, hospital records, etc. The problems are the same. It's a won't share, can't share problem. But in this example, in these use cases, there are some additional problems that you have to solve at the same time as the privacy problems, the won't share, can't share. And by that, I mean understanding that you're working with commercial organisations. General practices are businesses. They are not government. They have different drivers. They have different risk assessment models that they work to. And certainly the logistics of how do you accept or set up data flows where you can receive data from many thousands, hundreds, thousands of independent organisations. So a great many number of relatively small data sets that you have to figure out how to suck into a system to do linkage, PPRL linkage, and then deal with the results. So there are those challenges. So conscious of time, I'm only going to focus on one of those, which is the use case of Lumos. So Lumos is a project being run in New South Wales that attempts to, by New South Wales Health, attempting to link general practice data from the state of New South Wales to secondary care data. So and specifically to the master linkage map that's been created by the New South Wales Data Linkage Unit, Cheryl. So that's the model that we're working to, or that this project, sorry, is working to. So the trusted third party in terms of linkage is the New South Wales Data Linkage Unit, Cheryl, and the model there is to link to many general practice datasets to the New South Wales master linkage map, and in that way you would achieve vertical integration of general practice data, not just horizontal. In terms of linkage quality, in this particular case, they were very lucky that the linkage quality was able to be assessed through an early proof of concept, where name identified data from general practices, a select number of general practices, were able to be released, and by linking that using traditional methods, we could compare the linkage quality of PPRL against traditional methods. And that isn't always the case, of course. And other methods for trying to maximise quality have really been by trying to maximise the quality out of the master linkage map, which is linked using name identified data. In terms of challenges, as I said before, the logistics to roll out Lumos required purpose-built infrastructure and having to work with middleware groups, so organisations, commercial groups that are already nested inside general practices and have software and systems inside general practice. Other challenges that are being overcome as we speak is the scale out, that you want to capture tens of hundreds and possibly 1,000 or so general practices across the state. So how do you scale out to multiple practices? And also an ongoing problem of how do you monitor and assess linkage quality. And it's really not just linkage quality, it's also data quality, noting and knowing that data quality can vary over time, but also vary substantially from one practice, general practice, to another. Pardon me. And so that's it. I think, so in conclusion, I think these are just three different types of use cases where we are currently using PPRL as a way of accessing effectively hard to get data sets and enabling research. The PPRL methods that are being used in these use cases complement traditional linkage methods. They're not replacing traditional linkage at all. We're trying to leverage as much quality, in fact, out of the components of the linkage that already use traditional methods. The software we've developed in-house at Curtin and is available and is being used in these projects. And I guess I should say that PPRL methods generally are evolving. They're not set in concrete, and our methods and our implementation certainly isn't set in cement. And there are always developments that are being done and can be done to improve security and performance. So it's an evolving space, and those methods, as they evolve, we expect to implement and roll out into some of these use cases. And again, in terms of assessing quality of PPRL, in some projects, in some instances, we've been able to assess quality, and I'd refer you to Sean's presentation on those results. But again, we're always looking for opportunities in which we can assess and evaluate the quality of PPRL methods against other methods. That's it. I guess the only other thing is acknowledge my co-authors and our champions and the custodians and the projects who have allowed us to kind of work in that space and just see how we go in terms of using alternative methods in order to facilitate research. That's it. Thanks very much.
Many thanks for this great presentation and the interesting examples. We have plenty of time for some questions, and maybe we can even return to some questions concerning the first talk a little bit later. First question from Rachel Shipley from the UK is to Anna. Anna, when you linked the name spine in the first example, did you see any conflicts between the clear text linkage and the encrypted linkages?
Yes, well, yes and no. So we've actually done some work with the West Australian Data Linkage Unit on looking at comparing named and non-named linkage. And there are some linkages that there's a lot of overlap, which is very encouraging. There are also some links we have found with PPRL that we haven't found with clear text, and vice versa. And when we've drilled down to some of those, how is that possible, you might ask? And that really has to do with just nuances in probabilistic linkage. It actually has to do with blocking. That slight variations in blocking between one method and another was sufficient to not bring records together, irrespective of how the comparison was actually done. So it was a blocking issue that caused a slight difference in results. Not sure if that quite answered your question.
I think so, but the question has a second part, and the second part is, how do you resolve these contradictions?
I'm not quite sure I understand. So it's not an either or. So we're using PPRL as a solution. So the contradictions exist when we run comparisons in order to understand the difference, but in operational linkage. So these are live projects, all of them. There are no contradictions. It is only one answer that's derived from one of those methods.
Okay, many thanks for that, Anna. Josie, if you allow, we have two questions concerning your talk, and we have time to consider them. Can you unmute yourself for the answer? Thank you. First, have you considered other approaches than matching keys for the linkage operation in general?
Yeah, so regarding match keys specifically, we are thinking of doing a research project that converts our derived agreement from categoric to more of sort of like a linkage weight, and potentially making it seem a bit more probabilistic. With regards to the privacy, other privacy preserving linkage techniques, we're kind of, we don't decide the privacy preserving technique for this. So we are limited because the National Cyber Security Centre of the UK recommended hashing. So the data had to be hashed. We ourselves would much rather do trusted third-party linkage, and that is kind of what my team tried to provide. But in this case, NCSS wanted hashed, hence why we used the hash data linkage algorithm.
Okay, Josie, we have a final question, and the final question concerns the standardization. Did the parties providing the data, did their own standardization using the same rules everywhere, the same procedures? What has happened to, before you hash, what has happened to the data on each provider side?
Yes, so there was initially several weeks worth of work just agreeing what the cleaning and standardization would be. So that's where the hyphen gate issue came about. Moving on from that, we then we had to make sure that we were following those rules in the same fashion, so that for the same input, the data providers would produce the same output that we did. And this involved so coding the standardization and derivation and cleaning rules independently. And then we produced a synthetic data set, which each of the data providers and ourselves then put through this code, and we ensured that the results were the same. And in fact, we had quite a lot of problems with the double metaphone derived variable, as since our data providers were coding in SAS and we were coding in PySpark, it took us a very long time to sort of harmonize that. And in the end, I think that variable is only in harmony 99.9% of the time. And there's that 0.01 of inputs which actually end up with a different double metaphone hash, which we never managed to solve.
Thank you very much for that interesting detail. I would like to see that in a footnote. We have a final question for you, Josie, and that's how you measure recall in your application. Yeah,
so we calculate both precision and recall using our estimated number of true positives, and then for, I cannot remember my error grid, either true positives and false positives, or true positives and false negatives. So we did clerical review to estimate these numbers. So the number of estimated true positives that we made and false negatives that we made was calculated by clerical review on samples of our match keys. And then our false negatives and our true negatives were done using clerical review on that sample of 600,000 unmatched records. And then we used our error grid to calculate precision and recall using that information.
Thank you very much for that, Josie. We have no time to answer the remaining questions. We have to switch to the remaining talk. The final talk will be given by Thilina Ranbaduge, which is a computer scientist working at the Australian National University in Canberra. And we work on record linkage for a long time. And he will present something on one of the most interesting and complicated problems in privacy preserving record linkage, and that is missing data on the identifiers. Thilina, your screen.
Thank you, Rainer, for the introduction. Hello, everyone. My name is Thilina Ranbaduge, and today I'm going to present an experimental evaluation we conducted on different binary encodings that have been proposed for privacy preserving record linkage, and to evaluate how they perform in the presence of missing data. This study has been conducted together with Professor Peter Curtin and is funded by the Australian Research Council under a discovery project. Before we move on to the actual details, I would like to explain what is actually meant by privacy preserving record linkage. So privacy preserving record linkage is a process used in data integration where we link different databases and try to identify similar records that belongs to the same entity. And we need to make sure that the linkage is conducted in such a way that no information about the entities that are represented by these records can be inferred. This requires the data used in the linkage process to be either encoded or encrypted. And the outcome of the linkage process is a set of matched records, which is provided to data consumers for different data analysis processes with their corresponding microdata. Because there is often a lack of common entity identifiers across the databases to be linked, the linking of record is commonly based on personal identifiers known as COSI identifiers, such as first name, last name, address detail, or date of birth. And due to data quality issues, such as errors or variations in such COSI identifying attributes, approximate similarities are needed to be calculated between them, and pairs of records that are highly similar are usually classified as matches. Hence, any encoding or encryption method used in PPRL must facilitate approximate similarity calculation between sensitive values without the need for sharing the actual values, such that no adversary can learn any sensitive information about the entities in the databases that are being linked. So in general, PPRL techniques can be categorized into two: perturbation and secure multi-party computation. Secure multi-party computation techniques are provably secure, but they often incur high computation and communication cost. And on the other hand, perturbation-based techniques are generally more efficient than secure multi-party computation-based technique, but have a trade-off between linkage quality and privacy. One widely used perturbation technique for PPRL is binary encoding, where attribute values are mapped into the binary space for calculating similarities between records. So binary encodings are shown to be popular for practical PPRL applications because they have been easy to implement and also allow efficient similarity computations between records. And in this slide, we show such popular binary encoding technique using PPRL known as Bloom filters, where attribute values in records are encoded into bit vectors, and similarities are calculated on those bit vectors based on the number of 1 bits they have. However, one problem with such encoding technique is they require the COSI identifying attributes used for encoding to be complete. And this makes the use of such encoding techniques in real world challenging, as real data often contain missing values, which is a major data quality aspect that so far has only seen limited attention in record linkage. And missing values can occur for a variety of reasons, ranging from equipment malfunction or data items not considered to be important, or even the refusal of individuals to provide information, for example, when filling in web forms or answering surveys. If records have missing values in the coarse identifying attributes used for linkage, then the similarities calculated between records will likely be lower, potentially affecting the final linkage quality. And alternatively, those records or coarse identifying attributes that have missing values are not used for a linkage, then linkage quality will again likely suffer. So in this study, we aim to evaluate several binary encoding techniques that have been proposed in the context of PPRL and measure how their linkage quality changes with different numbers of missing values in data. So we use 3 different encoding techniques in our evaluation. The first one we used was cryptographic long-term key, which was initially proposed as a method that allows error-tolerant linkage of sensitive values by encoding multiple coarse identifying attribute values into the same Bloom filter. And CLK also provide improved privacy for sensitive values that are being encoded compared to attribute level Bloom filters where each attribute value is encoded in an individual Bloom filter. The second technique we used was the record level Bloom filter, which was proposed as an alternative to CLK to encode values from several attributes into one Bloom filter per record. The difference between CLK and RBF is that in CLK, all attribute values are hashed into the same Bloom filter, while in RBF, initially, one attribute level Bloom filter is generated per quasi identifying attribute, and then a certain number of bits are sampled from each attribute level Bloom filter and then combined into a one long bit vector generating the record level Bloom filter. And as the third technique, we used a recently proposed hashing-based encoding method known as tabulation min hash-based binary encoding. And similar to Bloom filters, tabulation min hash encoding technique encodes sensitive values into bit vectors. And this method uses locality sensitive hashing methods of min hash, where hash values are used to look up randomly generated bit string in a list of tables. And to generate a bit vector for a record, the sensitive attribute value of a record is first converted into a qgram set. And for each of the bit position in this bit vector, a random bit string is selected from a previously generated hash table based on the min hash values generated from that qgram set. And the least significant bit is then used from each of these random bit strings and which are concatenated together to generate the final Bloom filter. So in terms of data sets, we use 2 dataset pairs that are extracted from the real voter registration databases from US state North Carolina. And these datasets contain 100,000 and 500,000 records. We use first name, last name, street address, and city as the set of attributes in our evaluation, and where the records in these dataset contain value changes and variations due to individuals being changing their names and addresses. Also, from these 2 datasets, we generate 3 different variations of database pairs, which are containing 0%, 20%, and 50% missing values. And the missing values are introduced randomly into the records in these database pairs, assuming that the data is missing completely at random. To evaluate the linkage quality, we use standard linkage quality measures, precision and recall. This slide shows a summary view of our findings. And as you can see in here, when the databases are complete, all the encodings perform well in terms of precision and recall. However, as we increase the number of missing values in record, the linkage quality drops considerably for all the encoding techniques we evaluated. And as mentioned in this slide, we have seen a 10% to 25% decrease on average in both precision and recall for all encoding techniques. And out of all these 3 encoding techniques we have used, we have seen CLK tends to provide a bit more false positives than the other encodings. And this is because similar values in different attributes can potentially generate the similar CLK Bloom filters, which are potentially classified as matches. And due to they have higher similarities, and this tends to lead to a drop in the precision compared to the other encoding techniques. And while in terms of recall, we saw tabulation min hash based encoding resulted more false negatives compared to other encodings. we seen that this is due to the Jacquard similarity resulted by the tabulation in hash-based encoding to be lower than their actual Q-gram similarities if the corresponding record pair contains missing values with some variations in the other available attribute values. And to conclude this presentation, we have conducted an experimental evaluation of different binary encodings proposed for Prism record linkage and evaluated their linkage quality in the presence of missing data. And according to the experimental results, all 3 binary encoding resulted lower linkage quality, and when the number of missing values are increasing in the data sets. And this highlighted that we need novel encoding techniques which are robust for missing values in data. And it can be mentioned that in linkage projects, they should look for stable attributes without missing data in order to avoid reduction in linkage quality. But by adjusting the decision rules or matching weights in the linkage methods would potentially help to overcome the challenges of missing values up to a certain degree. I hope I have described our experimental evaluation on different binary encoding techniques clearly. And if you have any further questions, I'm happy to answer them now. Thank you.
Many thanks for this presentation, Thilina. As we both know, this is a really hard problem in practice. Up to now, I think we have no direct question to your talk. Therefore, I'm asking 2 questions. The first question, it's nearly impossible to impute indirect identifiers such as names or whatever, and therefore we can use that only for indirect some identifiers such as age or income or something like that. Do you have any idea on that?
So in PPRL context, I don't think imputation actually works. But if you can somehow impute the similarities by using other available attributes, that might be able to help. Such as there's one approach by Chi and others where they try to impute the similarities of if the records are having missing values by using the local neighborhood that belongs to that particular record, such as census records. So we recently did a research on these aspects where we tried to come up with a way of combining different encoding in the sense record level Bloom filter for attributes such that even missing values are present in records. Somehow we can calculate the similarities by adjusting their weights. And we have seen some improved result, and this research is under review at the moment. So hopefully we'll see something soon from them.
Okay, many thanks for that. Tina, the second question is, I haven't got really the details on how you computed the standard errors on the estimates. Can you repeat that in more detail a little bit?
So I calculated the errors based on, so this is just showing the standard. I hope you are referring to the standard deviation.
On the...
Yep, so I'm just using the, so the results are showing the average across all the experiments that I have conducted. So it's just showing the standard deviations. The results are across all the experiments.
Okay, many thanks for that. So we can go back, Thilina, for the last question for Josie, which is still on the list. I hope Josie is still with us. And if you unmute yourself, Josie, the last remaining question is, are you using special, not in the open software to generating the hashes? How you generate the hashes? Which software do you use for that?
So it's different for us and our data suppliers. So we code things in PySpark. So we've got the SHA-256 hashing algorithm that we code ourselves. And then at the moment, DWP and HMRC are coding this in SAS in their Oracle platform, but following the same algorithm.
Okay, Thank you very much. Thank you for all speakers. Thank you for being here, and hope to see you soon in a different context. Bye.
Thank you.
Thanks, everyone.